In this video, we're going to learn about another simple calculation we can do to scale variables so that we can plot them more readily. One of the variables we love a lot as meteorologists is this idea of absolute vorticity. Vorticity is a measure of the amount of spin in the atmosphere. And as a result of that calculation, the values are pretty small. They are on the order of 10 to the minus fifth. Now, we can plot that up natively, but then if we want to label those contours, that would not be, it wouldn't look as good. And so one of the things we can do is we can just do a simple multiplication factor to be able to then scale this variable appropriately. And so the variable that we want from the GFS is our absolute underscore vorticity underscore isobaric. This variable is only available at a couple of levels. And so we don't need to worry about subsetting it for a particular level to do our calculation at this point. But basically what we want to do is we want to replace the values that are within our absolute underscore vorticity underscore isobaric with those same values multiplied by 1e5. And to multiply by 1e5, as is described in the handout on page 4, this is like multiplying by 1 times 10 to the fifth to basically bring our vorticity values into whole values to make plotting a bit easier. And so we are currently using the same script, same notebook that was this thickness calculation notebook. And so I've still kept this active, but you may need to if you're viewing this on a second day when you haven't run this before. Just go ahead and quickly rerun those first two cells. And then come on down here and we can run our cell to scale our absolute vorticity by 1e to the fifth or by 10 to the fifth. Now, because it's doing a couple of different variables for actually a number of different times, this is taking just a bit of time to run. As that's running, let's go ahead and look at what is our plot. And so our plot here, we're going to do filled contour plots of our absolute vorticity isobaric from 500 millibars. And because we have not subset our time, we need to actually change this to plot underscore time. And then we are going to contour values from minus 40 to 41 by 2. And we're going to do that so that we use this color map that we're going to use, which is our purple-orange or pew-orange, pew-or, and we're going to do it in reverse order so that we have the colors as we want them. So that then kind of the clear or white area of this color map is then right in the center of our vorticity values. But what we're going to find is with absolute vorticity, we primarily have one type of value, and that will be a positive value in the northern hemisphere. Along with our absolute vorticity, we're also going to plot geopotential height at 500 millibars. And again, we're pulling this from our data set, so we're going to need plot underscore time. We're going to contour it every 60 meters as per usual. We're going to make that black and solid line types. Then we're going to add both of those things to our map panel here, and then plot it up. We still haven't quite finished here, so we're going to go ahead and run this cell and see if we can get this to finish and get a map plotted. This is one of the reasons why it might be best to actually subset for time. And so if this happens to you, one of the things we can do is actually hit this stop button. It will stop the process that is going on here. And then we can go ahead and say metpy select time equals plot underscore time. And something we're going to want to do then is pull up this plot underscore time to this cell, and then rectify a few things here. Now, because we're going to subset for our absolute vorticity, we're going to go ahead and make that none. So actually what I'm going to do here is, since it doesn't seem to be stopping, is I'm going to go up here to kernel. I'm going to restart and clear all my outputs. So if you ever run into a problem where something seems to hang, sometimes going up here to kernel, restart the kernel and clear all outputs will get us back to a square position. So since I restarted the kernel, I need to rerun these first two cells. Those ran pretty quickly. Now we're going to run this with our subset for subsetting for time. And then we're going to go ahead and plot it up. It's taking just a minute here because it's doing the color fill plots, which is a bit more involved. And here we go. We see our 500 millibar absolute vorticity plot. And you can see that the values, if we look down at our color bar, are primarily positive. That shouldn't be surprising since we are in the northern hemisphere where the values of absolute vorticity are largely positive because of that Coriolis parameter. But we notice in the center of some pretty strong vorticity, we kind of max out on the top end. And so when you see something like that, we can actually then change our contour values, now going from -50 to 51 by 2, and seeing how that may help our plot and reduce those maximized areas. Sure enough, we overcame that now, and so now we don't see those white spots going on within our maximums, and we get this overall nice looking plot, and where we see positive vorticity, typically in our troughs here, and negative positive vorticity in this trough, and we see only the little hints of negative vorticity in what is almost an anticyclonic area, and some of that may be due to stuff that's going on in the model related to some jet streams, for example. But our absolute vorticity is generally positive in the northern hemisphere. And on your homework assignment, you're going to have to look at a map of both absolute vorticity and just relative vorticity and be able to describe some differences there. So we can see that scaling our parameters isn't too hard, right? It just becomes a simple multiplication problem. And so depending on what your variable is, you may or may not need to scale something to get us into these whole values here so that our color bar looks nice and that if we were going to contour something, it would look nice as well. That's it for this video. Thanks for watching.